Session with Professor Michael Roeckner from Bielefeld on random attractors for stochastic porous media questions.
Yeah, thank you very much. So it's, of course, again a pleasure to be in this fantastic building, fantastic institute. When I thought about the topic of the talk I should give here, I tried to find something which I hope is appealing to both communities, the PDE and also the SPDE community. So at the end, what I'm talking about is quite simple model. We are presently working in a much harder case. Parts of the talk will be boring for probabilists because I give all the definitions of what is a random dynamical system, and part of it will be more boring for the analyst because I'm showing some estimates that they might know even better than I do. So, but I am happy for all kind of feedback from the audience. So this is joint work with Benjamin Guest, Paul Lescaut, Wolfgang Bein. So Wolfgang Bein is a numerical analyst in Bielefeld. Paul Lescaut, most of you might know, former student of Paul Maria Wein. Benjamin Guest is my student. He's just in his first year of his PhD thesis, and he really made a very nice contribution to this paper. And he's now working within his PhD thesis on the much more difficult case. So look at this object of desire. That's the stochastic porous media equation. And we are just looking at the simple case of additive noise. And he's working on the much more difficult case of multiplicative linear noise. Of course, you have to color it in higher dimensions. But nevertheless, that is much, much harder. But it seems now that he's on a very successful way. So he's solved the first steps. And when he's coming here in June, I hope he can already report on this much more difficult case. OK, so that's the structure of the talk. So first of all, I recall all the necessary definitions, and then of what is a random dynamical system. And then I will explain to you what is the random dynamical system coming from the porous media equation. So that's sort of the one that comes from an SPDE in a canonical way. And then I will explain you the main results and then the idea of proof. And so let me start with the definitions. So random dynamical system is a metric dynamical system. Is you're given a probability space and you are given mappings for every t in the real numbers. And these mappings are measurable in the two variables in t and omega. At 0, for t equal to 0, it's just the identity, and you have the semigroup property. And they should leave the measure of the probability space invariant. So classical example, you look at the two-sided Wiener measure. So we look at the Wiener measure on R, not R plus. Yeah? We take the whole real line. And then we look at the classical Wiener shift. And as you will see in all of this talk, this omega, which of course probabilists think of it as random, and it is random because there's a measure that sits on it. But this omega, when I study the equation, will really be fixed. So as you will see in a moment, by some standard method, you can do this. So now here, what is a random dynamical system? So given a complete separable metric space HD, and you have such a metric dynamical system from before, you have these mappings t to t, then so such a random dynamical system is simply a map from R plus cross omega cross H into itself. So that means, so these are mappings in this variable with values in H, and I look at this mapping for given omega and for given time. So if I look at 0, this is the identity. And otherwise, it satisfies the famous co-cycle property. So that means if you think of it, for instance, as a flow, the difference is that the omega moves in the time that elapses after you do the first application of the flow. So that means you think of this omega as a fixed thing, so not dynamic in time, a fixed thing, and the only dynamic you put in here is the shift, is the Wiener shift. So that means you apply the map to H from H to H, the time S elapsed, but the omega has changed in the meantime. And then you apply the flow for the new omega, the one after time S, and then you get it's the same as do this mapping all the way, in the time from 0 to t plus S. So that's the famous co-cycle property. And of course, it should be continuous map from H to H. And what is very, very important that this is really true for, if you have such a set omega, it will not be the full Wiener space that I wrote before. It will be prescribed by measurable subset thereof, this omega later on. But what is important that this is true for all t, s, and all omega, and it should be continuous for all t and omega as a function from h to h. So no zero sets allowed. Yeah? Okay, you can say, oh, this is true almost surely, but this just means you single out a certain omega, which is a little bit smaller, and then you have to do it for all t, s, and x. That's very important. Yeah? So when you don't do that, then it's non-rigorous, and you can prove a lot of things, but not the things we really need, because this co-cycle property is absolutely crucial to be true for all t and s and so on. Okay, so now quickly, what is a random set? So if you look at the mapping from omega to the power set of H, so the system of all subsets of H, you call it measurable. If you for every point x in H, the difference, I mean the distance from x to this random set is measurable in omega. So that's the first definition. And then you look at the distance, which is a usual thing in this area. Of course, I will give references later, but I would really like to recommend for all the general stuff the book of Hans Kraul, where this is all explained beautifully, and of course the even older book of Ludwig Arnold. So here's what is sometimes called one-sided Hausdorff distance. So the distance from A to B, so you really think of it directional from A to B because it's not symmetric. You take for an x in A the minimal distance to B, and then you take the soup of all those distances. So the easiest example is if you take Russia and you take Germany, and somebody in Germany measures this distance, it will be much, much smaller than if somebody in Russia measures this distance. It's because somebody in Siberia will have a long distance to Germany, while somebody in Bonn will have not such a long distance to the first point he crosses the Russian border. Yeah? So that's exactly the point of this distance. But it's the right distance to consider, and usually, as usual, we abbreviate. So here, this is just the definition, it's just the distance of the point, so that's the usual thing. K is also called a random set then, and if you have two random sets, A and B, you say that one absorbs the other if for P almost all omega, so here there is a zero set, but again, I mean, in most cases, you again take a smaller set and then things are good, but for this it's not necessary. I mean, for this, for the general, you have to, but here it's not necessary. In principle, this is enough for P almost all omega in most cases. So what does it mean? So you have a random set A omega, it absorbs now the other random set in the following sense. So you look at this set, but not at omega. So let me see. So this is the positive x, this is the minus from your side. So you go back in time, yeah, with the set. B, you look at this B at the omega in the distance by this theta minus t. Then you apply your flow up to t, you get back to 0. And there it should be called by A of omega, so sort of being at 0, so times 0. Omega is not shifted. Okay, so it absorbs this for all sufficiently small t, so we have a minus here, so there's an absorption time. So if you go far enough back, then you will be in there, and then from all times even if you go further back. Okay, so and then A is said to attract B if you do not have that this is inside, so this is not inside A, but it is close in this half-sided Hausdorff distance. So that's the attraction, or that's the notion of attraction. Okay, so as you can see, it's different from the deterministic case, because in this deterministic case, everything coincides, of course, with what you know in the deterministic case. It's really, therefore, also called, sometimes called the backward attractor or something like this, because you go backward in time. But this is the right thing to do in the stochastic case. So here's the definition of a random attractor. So it's a random set. So you're given a random dynamical system. You're given a random set. And if for almost all omega, A of omega is compact and is invariant under the flow. Now, of course, now in the proper sense. So you apply the flow, yeah, and then the time t elapses after you have done your application to the set. So it should be A at the later omega. Yeah, so it's very natural. So this should be the same. So that's invariant. And of course, it attracts every bounded deterministic set. Yeah, so we defined even for attraction for random sets, but a random attractor has to attract every bounded set which is deterministic. So that's a random attractor. And what is very important in this terminology is not mine, it's the one of the experts in the area. It's always compact. So it's always a compact random attractor, but it's put simply in the definition. Okay, now if you think how can you construct random attractors, then you come up immediately with this definition, which is technically a very important one. It's really not so difficult if you look at it. So if you have a random set and think, okay, so and what you do is you go backward in time with this set, go again backward, then you apply phi up to 0. Of course, then you have to start here at the right time here. Yeah, you go up to 0. Now I'm at 0, and I do this for every fixed t, and then for all my random sets in the past, all of them. Yeah, then I put them to 0. I take the union of those up to some time big T. Okay, and then I take the closure, and then I do this intersection over t, because you can see this is decreasing in t. So you go further and further back, you take all of them and you look at the limit, and you take the closure. So that's the omega limit set. That's something like a random attractor if it's a compact set. Yeah? If you could do this at least for all deterministic sets here which are bounded. And so the next theorem is not so surprising, though technically not so easy to prove, and that is really the main I think, result for the theoretical part of the theory. So that is in this famous paper by Hans Kraul and Franco Flandeli from PTRF in 1994. It's highly quoted if you look at the Matzai-Net. There are other papers also with Arnaud de Bouche, where not very much later, but I mean, I think it was there, where at least we found it in the proper, formulated in the proper way. So you have a random dynamical system, and assume you can find a compact set which absorbs every bounded set B. Yeah? So absorbing every bounded set C. That's enough to make sure that this omega limit set, when you take the union of all bounded sets, really is a random attractor and is compact. So that's the sort of the thing you would, if you want to write down the random attractor, exactly this, remember? You look what you get at 0 if you go very far back for every bounded set. Go here. And then you take this union of all those, so this attracts any guy from the past which is bounded. So that's a really very intuitive way of understanding what is a random attractor. And of course, this has to be compact, and I think this is very nice in this theorem. You just have to find one compact random set that absorbs every deterministic bounded set. Then this thing you would expect to be the random attractor really is the random attractor. Okay, so now, So now I'm going to the special random dynamical system that I'm considering here. You have the equation there, always to remember. And since it's fashionable now, I would like to make, okay, maybe I'll make the remark a little later. Okay, so we look at this, what is stochastic porous media equation. And we start at any s, of course. And most of the proofs I take s equal to 0, which in the idea of proof later on. But of course, you have to start at every s. And we take a very simple noise. But the most important thing is a function valued noise. Everything is trivial. Also, if you look at the multiplicative case, it is trivial if you take Brownian motions which are just in R1. So these are not constants, these are functions. If these are constants, it's more or less nothing to do. Yeah? And everything is very, very easy by general theory. But there are functions. So in particular, in the multiplicative case, it is very, very hard if these guys are functions. Okay, so this is, but nevertheless, it's finite dimensional. So, you can say finitely many modes of the Brownian motion, but they are function valued. And this is, of course, physically what you would like to do, because you would like to perturb your system not by some random vector, random numbers. You would like to perturb it over the space by random functions, yeah? By randomized functions. But for simplicity, we take here, no, it's not only for simplicity, to be honest, we take here just finitely many modes. If we take here infinity, and this is the strange notation is here, you can think of this as some operator acting maybe on a Brownian motion with infinitely many variables, but it projects down just to finitely many. So it's a very nice Hilbert-Schmidt operator, even with finite range, the best you can hope. It can be generalized in some cases, and I will tell you a case where this is just a Hilbert-Schmidt operator. So this can have infinitely many, but for very singular phi, you cannot. So if you take not singular, but let's say phis which are not of polynomial type, you cannot. Then we really have to be careful here, and we take finitely many of them, in particular in the multiplicative case, and we see this as a test case for the multiplicative case. Yeah? So we did not go to the most general conditions for the additive case. Sorry? For existence and uniqueness, just a second, yeah, we can do very, very general phi, but in this talk I will take special ones, more special class, okay? Good. So this is the noise. So they're independent Brownian motions, and there are some functions. You can assume that these are in H1. It's H10. It doesn't have to be C1. It's just for simplicity. Okay, and we look at the canonical Wiener space. So, but please, of course, path defined for all times. Okay, so I abbreviate this SPME, so that's a stochastic porous media equation. And here are the assumptions that we use that I'm going to use in this talk. So phi is just C1. Phi of 0 is 0 for simplicity, otherwise you always have to be careful to shift in the proper way. I want to avoid that. And phi prime is strictly positive almost everywhere. So the classical case where this is, for instance, the power 3 is inside. Yeah? So only almost everywhere must be strictly positive. We also have cases where this is not true, so we can also handle phi which are constant for, but I will not talk about this today. It's too complicated to explain then the proof in that case. Okay, and then we have the usual condition on phi, so it must have sufficient growth here. So there is a p bigger than 1, so that is s times phi of s, so it's sufficiently big to have coercivity, otherwise the equation will not have a solution for all times. And the other thing, we need phi is polynomially bounded itself, and we need a bit more the derivative polynomial bounded here with p minus 1. So this should be basically polynomial by order p. But we need to formulate it this way because here we also have to control the derivative. Yeah? So this, of course, there's a lot of examples, but now there's one technical thing we discovered. Maybe it is known, but so far we could not find anything in the literature. We define this function because phi prime, if we have differentiability, we can define this function, and then we can sort of measure how monotone the phi is, because this will be, yes. Of course, we have here, by this, we have this is a monotone function, and we measure how monotone it is by this function zeta. Yeah? So if you define zeta like this, there's a simple exercise that you have this inequality. So that sort of measures the monotonicity. And this function zeta is extremely important, as we will see later, and I would like to point out now, take this special case. This is the classical porous media case. I'm not doing fast diffusions here. My students are now doing fast diffusions, so using same things, but anyway. And then the zeta of s, you see, is this function. Yeah, you can just calculate from here. You get this function, you get p minus 1 over 2, so with this 1, it's of the order p plus 1/2. Okay, and that's known from porous media equation. It's a very important power that you should study of your solution. So therefore, I think so technically this is the cleanest way of using this fact, as we will see in a moment. Okay, so that's zeta monotonicity, and of course you can find many other examples of not just this one. And of course, if pi, the easiest case, p equal to 3, so we have here x to the 3, p equal to 3, this will be just basically s times, so 3, so you have s to the power 3 here. Then this will be, if you put 3 here, 3 minus 1, so it will be s times s norm in that case. Yeah? Or s absolute value, as real value things. Okay, so now I come back to your question. So if we just look at the stochastic porous media equation, existence and solution has been proved much more general than I'm talking about here. So we can do fast diffusion equation is inside, we can do these logarithm guys and so on. And the right paper to look at is the first one. The second one generalizes to very general phi. We don't need that phi is continuous in those papers. Here always assume even differentiability, as I said before. This paper is for non-continuous phi. Here phi is still continuous, but it can be of very slow growth. And the trick to do that, it's not maybe so original, but is to work in proper Orly spaces. And we did this in this paper. But the other thing I would like to mention, since it seems now popular to look at fractional powers of the Laplacian, we did this in very general situation. So for any operator, xt, self-adjoint operator, so that the corresponding Dirichlet form is transient. So of course you can put minus Laplace to the power alpha and the minus sign. So you can take fractional operators there as long as the corresponding Lévy process or up alpha stable process is transient. So that's very important. Otherwise it doesn't work. And we can take all of RD. Here I'm just working, and I forgot to say that, I'm just working on the interval 0, 1, not on all of them. But in RD, it can work on all of RD if D is bigger than 3, for instance. And for the alpha Laplacian, even if the alpha is appropriate even for other dimensions. So for dimensions 2, for instance. Okay, anyway, so existence and uniqueness is proved. This is not the point of this talk. It can be much more general. Okay, so now let me explain. This is not only the interval 0, 1. I was too restrictive here. So lambda is just an open set in RD here. Maybe I write this on the board. So the whole thing is on some set in RD. The arbitrary and of course is an open set. Let's say open and connected. So why do we call this lambda? I was asked when I gave this talk last week in Swansea. Analysts say omega. We are not allowed to use omega. That's the probability space. Sometimes the analysts say big O. But people from statistical mechanics, a finite vessel is lambda. And this is the background because we are interested, of course, in the statistical mechanics of the situation. Anyway, so now we have this stochastic porous media equation. And as you know, the stochastic porous media equation is solved on the Gelfand triple, where this H, which is the state space of the solution, is the dual of the Sobolev space of order 1. But the solution is for Lebesgue almost all times in the smallest space, so you really can apply a function to the solution, because solution is a distribution, but only a distribution to have continuity in T. Yeah, it's an H minus 1 is continuous. Let's call this H minus 1 as it usually is called. Yeah. In H minus 1, we have continuity in T of the solution. Yeah. But it is really for almost all T in time, for Lebesgue almost all T is a function in LP plus 1, so you can apply a function to that. So there's no renormalization necessary like in stochastic quantization. Yeah. So just to make this clear. Okay, so now I'm not going to use this general existence result I just mentioned, but I want to solve this equation omega-wise in the usual way. So if you have additive noise, you shift away the noise. So you write the equation for the difference. So you shift away this thing. You take a fixed Brownian path. So this is just a continuous path that you subtract depending on omega. So omega becomes a parameter. And then you write the corresponding equation for the difference, and you come up with this equation. You start at S, so this term comes in. And then this guy is simply you just subtract, you put it equal to y, and you add. So this will be for y the coefficient, and what has changed is now the phi is time dependent. By the way, the general result about stochastic porous media, you can phi depend on time. Yeah, that's not the problem. So anyway, so this becomes time dependent through this path. And what is not so nice that this path is only in R here, so the time dependence is only continuous, which is not so nice. I mean, if you think of parabolic regularity for nonlinear equations, you would like to find results, then if this is just continuous, then it's not, you don't find too many results in the literature. So we checked Vasquez's book, is not so much in there, Barbou's book, the new book is not so much in there. And so we had to do a few things by hand because the literature was not appropriate to what we needed. Anyway, so now I fix omega and I'm back to a deterministic equation, and I just solve this deterministic equation now, which is possible just by monotonicity methods. Yeah, so that means it's still, this R is harmless with respect to monotonicity. If you check monotonicity, then this just goes away. So that means the constants don't change, everything is fantastic. So you can find now for fixed omega, it's very important here that now we will fix omega. So this will be fixed in a moment. Okay, so for every such fixed omega, and for instance, in my book with Claudia about stochastic porous media equation, you just take the noise equal to 0. You find exactly the theorem you need to get this solution. So for any initial time, initial datum x, and any fixed omega, you find a solution in this space. So it's continuous, starts at S, it continues in H minus 1. And it has this local integrability property. Yeah? So it's LP in time with values. And remember the V, I write this on the board, is LP plus 1. So we have this triple, LP plus 1 over lambda. And then in the middle there's H, which is nothing but H minus 1 over lambda. And then you have the dual of this space in this duality. So you have to be a little bit careful. This is not LQ here, right? Because you do the dualization with this pivot space. So be careful.
Lambda is bounded domain.
Lambda is bounded open domain in this talk. Yeah. But for the, as I said before, we can do also unbounded cases. But in this talk, let's just take bounded, okay? Because I have to use Poincaré in a moment. Okay. Right, so then we can solve the equation. And now we can solve the stochastic equation omega-wise by just reversing the transformation. And I use this new notation, so to think of this really as a flow. So that is the initial condition. So xt now is this one, so it depends on x. And it is continuous function in x. So this is continuity of initial condition is, for instance, in this. It's not due to us. It's just you find exactly the right theorem in this book. So you have continuity here. So, and using this, we will now define our random dynamical system. This is nothing but the solution starting at x for given omega at s at time t. Yeah? So that gives me now these maps. Okay, and then this solves this equation. It's just transformed back. And now I start at s, so this term comes in. Okay, so now we define our theta t. So this is just a Wiener shift. And then this is our random dynamical system. You start at time equal to 0 at x, and you let the time run up to t. And that is exactly then phi t omega of x. So it's continuous in x. Everything is defined for every t and omega. And then by uniqueness of solutions, which is this one, yeah, this is not uniqueness in the stochastic sense. It's omega-wise, omega fixed. And whenever you work with random dynamical systems, of course, experts know you have to work with fixed omega. So therefore, it's very important to have then uniqueness now for the deterministic equation. So this is here. And then it's another one by uniqueness. You have this. And then I leave it to you as an exercise by these two properties of our solutions. This will satisfy the co-cycle property, important co-cycle property. So we have a random dynamical system. And here's the first main theorem under the above conditions on QW and phi. Remember the conditions on phi, so the strictly positive polynomial growth, and then growth at least s times the function growth at least like s to the power p plus 1 minus a constant to have enough coercivity so the solution exists for all times. So, and this is, now I'm going to give you an idea of proof how to prove this, but we have a second theorem which some of you might be even more interested in, that in the special case where phi is this, more generally, we need the following monotonicity assumption, which is fulfilled in this case. So exists p bigger than 1, so bigger than 1 we need here, then eta positive. So we have this monotonicity, so that we measure monotonicity in a different way here. And then this again should be of polynomials. And this we can do for arbitrary Hilbert-Schmidt operators. So noise can be infinitely many function-valued Wiener processes. So that's a cylindrical Wiener process in this space. In this case, we can calculate explicitly the random attractor, which is not so surprising, because in that case, of course, you know, in the deterministic case for the porous media equation for phi, for instance, like this, at least, it is, of course, known, so this is not there, from Aronson result, that the whole thing decays very polynomially, yeah?
You know the out of dimension.
Maybe. These are all interesting questions, but I'm not going to address that. Okay, so in this case, in the deterministic case, you can calculate the random attractor, and in fact, it's one random point only. So what you do there is very simple, and you don't need the whole machinery. Yeah? You just calculate this limit. So you solve the equation from a negative s to 0, yeah, for fixed omega, with initial condition x. And then you can prove that when s goes to infinity, this is a Cauchy sequence in h minus 1. Okay? And the limit does not depend on the initial point. And how do you prove this? I mean, you can look in the book that I mentioned earlier, so my book with Prévost, where we prove the existence of an invariant measure for dissipative systems, and we basically copied the proof of Giuseppe and Jerzy Zaptik in their book, 96 book from Cambridge University Press. They did it for the mild solutions, and we did it for the variational solution, and also for the deterministic ones. I mean, this is all inside this theorem. And we do not need exponential decay, so this is enough. And it's a bit more complicated than the original proof of Giuseppe, but the idea is the same. And then you find this way, the solution, the distribution of this random variable in omega is exactly your invariant measure of the system. So that was a known thing to do. It's a bit more complicated because here you only have polynomial decay, but I mean the techniques are there, so it was not so difficult to prove. So there exists, just a second, there exists an invariant measure, and the same thing if you now don't look at the distribution over omega under the probability measure, but for fixed omega, this gives you exactly the random attractor. You can just check this is the random attractor. It's just by bare hands, nothing to, no magic. Yeah? It's very simple. And I'm grateful to Franco Flandoli who pointed this out to me, that if you can prove that this limit exists and is independent of x, that should be the random attractor. He told me in Oberwolfach some time ago, probably he remembers very well. And it's really true, so then in this case it proved directly. Yeah? So in that sense, it's not such an interesting random attractor. It's just one point, but it's nice to know for this very classical equation that you have this. And we expect that in other cases, this will not be 1 point, and so there you need the machinery. And now let me come back to 3.1. So really, for the general phi's, we have to apply the machinery to find the random attractor, and then we don't know what it is at the moment. Yeah? So then, of course, interesting questions follow. Can we say something about the structure, about the Hausdorff dimension, whatever? So that is, of course, another step. Okay, so now just to show you an idea of proof. So let us just look at this particular case, so at this phi. And you will see in the proof, I will set it up in a way that it can be done for general phi, and instead of this s to the sp minus 1/2, the zeta function, this is the special zeta function. You use the general zeta function that I have introduced before, and then the proof goes through. That's the observation. Okay, so we need to prove the existence of such a compact set, which absorbs every bounded deterministic set, almost surely, and we choose this set. So we take the L2 ball, and of course, remember, H is H minus 1. My process lives on H minus 1, so the L2 norm is compactly embedded in H. So if I take the H closure of this will be a compact set in H. So if you look at other papers about SPDE papers about random attractors, they normally use that the process is in L2, and they have, for almost all times, the thing in H1, and they use the compact embedding of H1 into L2. And so so in their framework, here would be H1, here would be L2, and now, sorry, maybe it's not good to see. Can you see? Okay. Anyway, so we use this embedding. So with L2, yeah, not P plus 1, but L2. So this is one thing. So that means this will be a compact set, a random set, and we have to determine the omega. Yeah, this k omega, the radius of the ball. That is what we have to calculate. And of course, if you think of absorption, I mean, you have to look at this guy applied to a ball, let's say in H minus 1, and you have to see how this ball develops, and that is captured in this guy, in this L2 ball, basically up to closure. But that is what you have to show. So we have to look at this guy, and then, okay, this is very easy to see. It's the same as this. So we just have to look at the solution of my equation for fixed omega started at x at negative time, and what happens at time 0. So we would like to have bounds for x, for fixed x, first of all, under the solution flow, if you like, in the L2 norm. We have to look at the L2 norm. The problem is that the xt is only a continuous process in H, right? So we do not even know, okay, it is for almost all t, it's in LT plus 1, but we have to show, I mean, that's really integrable in L2 and so on in order to make sense of the whole thing. But I will do this in a moment, how you do this, yeah? How you come back to L2. And in fact, there's nothing. We can prove that the solution for a fixed omega is, if you start in L2 all the time in L2, and it is right continuous in T. We cannot prove continuity in H minus 1. And I would like to ask the expert whether this is known for the classical deterministic porous media equation, that you have right continuity of the solution in L2. We cannot prove left continuity, but we can also not disprove left continuity in L2. Okay? But that's a major point here. Okay, so we have to control L2 norms. Okay, so now we fix the omega. So I look at the solution of my deterministic equation. So it's the same as this. As I said, this was the transformation, and I prove such estimates. Such an estimate. So this is sort of the standard thing what you have to do, which you know from other papers. In other situations, for instance, when here's H1 and here's an L2, is the same thing. You have to prove such an estimate in the stronger norm. So here with the minus alpha, and then this is allowed to be, of course, a random, depends on omega, polynomial. And why do I put polynomial? Is just because I'm lazy, because what you get from, if you prove this, what you get from here is that this gives you an exponential bound with on the development of yt. So if you start at some x in the very past and you let the process run, then it will at most deviate from this point exponentially with so in time. So that means you have to you can allow a polynomial to make it even bigger, because the exponential one will always take it back. So that is the result. And at the end, we cannot just look at one point. We have to take a whole H-ball in the past, which goes. So that means we have to control an H-ball. So we have to compare the weak norm with the strong norm. So we need the second inequality. And if you have that, then you can easily prove what we want. That really this nice, compact, random set really absorbs H-balls from the very, very distant past. Okay, so this is the thing. This is not due to us. This is exactly in the paper, for instance, of Landoli and Kraul. So we just have to check. So the point here is that we, from this equality, I will only prove this inequality. It's the more difficult one, as you can imagine. And so in particular, if you have this inequality, I leave it as an exercise. So the random polynomials, by the way, these are random functions, and they are polynomial in T only with probability 1, because here the Brownian path will go inside, so this is only true, and the powers of the Brownian path and so on. So this will be only polynomial for almost all omega, but I can fix that set. I look at all Brownian paths so that this is true. This is my set omega 0. And for such omega and omega 0 with full probability, I can prove, this I leave as an exercise, from this inequality you can prove immediately that Yt is right continuous. Just from this inequality. Of course, you have to use it in full strength. I mean, if you now come along and say, I integrate from 0 to t this inequality, is a bad idea. You have to integrate from s to t and take s as your point where you would like to prove right continuity, and then you get exactly the right estimate. And then it becomes very easy. Okay, so we get right continuity. So now let me explain a non-rigorous proof of the first inequality. So try to remember this inequality. So I will end up there. And okay, so first of all, we write our equation. So that's the solution of this, yeah? So that I fix omega. Here's a fixed omega. Everything, now omega is always fixed. Yeah? I just use a short notation of this complicated thing by just yt. Okay, so how do you do this? Of course, you multiply by yt from the left. You take inner product in L2. So you get 1/2 of this guy is equal to inner product of this guy with y2, with yt in L2. Yeah? So there's just the usual energy approach. Well, of course, this is already not justified because yt is not in L2, full stop. It's only for almost all t, so you have to be careful whether you can do that. But there's not such a, so far, of course, this can be justified quite easily. Apart from maybe everything is plus infinity. You have to do something. Anyway, so now the next step is we just plug in the definition of yt. So this is xt, so yt is this minus this. So I just write this as xt minus qwt. This comes from this transformation. So I just plug this in the linear part, in the first part. Okay, and now I have to estimate this and this separately, yeah, to get something like minus ytl square minus constant plus a polynomial. Okay, so now, so far it's not, this was only a little sin, just to ignore that yt is not in L2. Now here's a very big sin that people, that you would like to be tempted to do. So you see, you take this term, this was the first term here, this one. You take this term, and the thing you do, this one. The thing you do, you just take the Laplacian over. Okay? So you integrate by parts, you get minus sign. And here's a problem, because this is never in H1. You're not allowed to do that. But this is the big sin. Okay? So we just do that. In fact, this is true. This is a mistake. It should be LP plus 1 here. And you have xt to the 3 is in the right space, because the solution of the equation must be in the right space. Yeah? But it follows also from the proof. But let's just do it. And then we just resolve this by using the chain rule to the power 3. You get 3xt square gradient xt. But again, the gradient xt doesn't exist. Yeah? But you just do it. Okay, then you just you take the 2xt square and you write it like this, yeah, with the minus sign. And then the next step you do is you just put this back into the gradient. Yeah? So you get this. Okay? xt times xt bar. There, of course, you have to be careful. This, you would expect xt square here, but it's the same as this because we take absolute value by the locality of the gradient. And remember, this is exactly zeta of xt for the case p equal to 3. And I'm doing here only the case p equal to 3 for simplicity. So this function zeta pops up here. So there's hope that zeta of xt is always in H1, which is really true. Yeah? And this can be proved rigorously. But now what is very important, I have a sign here. You see, so there is my minus sign. And I need minus the L2 norm of the gradient of my yt later on there, and this will I will do in the next steps. You will see, not the gradient, the L2 norm. So now I go to the second term. So now I estimate this one. It's very elementary, so this is boring for the analyst, but just to show you the technical problems that you face. So we have this, and then again we just take the gradient over. So that means we have a gradient of the, so remember this is C1. Yeah? So this was C1, the gradient is no problem, but here we have a problem with the gradient x to the power t3 is no problem, but then to resolve it like this is a problem because this is not in H1, so that is purely formal, so heuristic calculations. And then you just put this back inside because you have the hope xt square, which is the same as xt times xt norm, is inside H1, so that should be okay. And then you have the other part, and now you can do the estimates, right? I mean, this you just estimate now by Young inequality, and you write this again because we have absolute value as xt times xt bar, so zeta is again appearing here for p equal to 3. And you take a small thing. Remember, in the other one we had minus 3/4, so the minus will survive. So this term will not harm the minus term. And then you just separate this one again by Young. You make this small and you make this big. Yeah, just to take 4 norms. So and from here on, everything is rigorous because one can prove really that this is an H1. And then we plug everything in. This was the first thing, was a minus 3/4, if you remember. The minus 1/4 gives you minus 1/2, and there was a 2 in front. So this survives, and the 4 term survives. And now it becomes very simple. We just estimate this by Poincaré with x to the 4 here. It's a right homogeneity. This is square, and your gradient square, so that gives you a 4. Poincaré gives you a 4. So this is very crude. You can do probably much better. This delta is very small, so you can as small as you like. I can take it smaller than the Poincaré constant there, which is positive, which comes in there. Okay. This term I just copy, and then I just estimate this below by the 2 norm. You see, it's very simple just by this elementary. I get a constant here, but the constant doesn't harm me. So I get this is less or equal to this guy. Yeah, I separate again. So this guy, and then this guy I just copy, this guy I just copy. And what I've done here, I've plugged back in the yt. So this is xt is this guy, and then I just estimate from below by this minus this. So I get another term here. But if you look at the whole thing, you get this is less than a negative constant times the L2 norm, exactly what we wanted. And here's something, and you see here the Brownian path in there. And the gradient is only a spatial gradient. Yeah, so it just differentiates the phi j's, so the beta j's just survive, and you get some powers of them. So definitely this is a polynomial in T. So that's it. So that's the non-rigorous proof. So the question is, how can you do it rigorously? And it's not so easy. First, you think what you can do. For instance, my friend Viral Barbu always tells me he believes in formal calculations. So if you can do something formally, it is always correct. I worked in quantum field theory, and you can do a lot of formal calculations there to convince you something is correct. But up to now, a lot of these formal calculations have never been made rigorous. Yeah? And sometimes the things suggest probably cannot be made rigorous as they are suggested. Yeah? So one has to be a little careful, and this is such a case where you really have to work unexpectedly hard to make this rigorous. And let me try a little bit to explain how we do this. Because it becomes extremely important that this operator is what we call a Dirichlet operator, so satisfies maximum principle. So therefore, in the general case, we really need from this operator generates a Dirichlet form. That means the semigroup generated by the operator is a submarkov semigroup. This becomes in very, very heavily. And so let me explain this too in this case. So what is the idea? The idea is, if I look at yt, which is an h minus 1, and I write down the h minus 1 norm, there's no problem. So by the chain rule, you have an equation, because the yt satisfies the equation. It's trivial. It's just the energy equation. But now we would like to approximate the L2 norm by the H1 norm by just putting this factor inside. So if epsilon goes to 0, so this is an equivalent norm on H minus 1, but it depends on epsilon, so I denote it by this. And of course, everybody knows if epsilon goes to 0, this increases to the L2 norm. Now you might think, okay, this is the normal Yoshida approximation. It is not the, you're right, but it's not the Yoshida approximation for the operator. It's really the Yoshida approximation for the form given by H minus 1 norm. That's very, very important. You cannot do it on an operator level. You really have to work with forms here, otherwise it doesn't work. You will see that in a moment. Okay, so then, for instance, in this paper with Feng Yu, we looked at such kind of what changes if you put an epsilon inside. And then if you write down the equation and you use chain rule, then you get this equation. Yeah? So it looks different from the previous one. There still is this. Now I look at the general case P. So before we had x to the power 3 there. Yeah? But I think now you can recognize this is now the nonlinearity, and this is called phi in the general case. Yeah? So just to put you back in the general case, you get an impression how you do it in the general case. Okay, so you just do this, and then you have this term. And now, first remark, if epsilon goes to 0, we work pointwise. So there's no eta formula here. And you see, this term is harmless if you look at it randomly, because if you can take expectation, this is expectation 0, this is expectation 0, this is gone. But pathwise is not gone. Okay, so you have to work with this thing. And of course, if you now you can see if you assume this to be C2, then if you take epsilon to 0, it's no problem. This just converges to the second derivative, so Laplacian of the Brownian motion in space. No problem. But it's C1. So we have to prove that this converges, this term. Yeah? And C1 case is really the interesting case for these random dynamical systems. And also we have to prove that if epsilon goes to 0, this converges in a reasonable way. And here I use the following trick in order to show that. So, and this is where I use Markov. So I look at this operator, and of course it's nothing but the resolvent of the Laplacian. If there's a general operator, you get the resolvent of this operator. Same thing. And you know that this is given by a kernel. It's not so important that there is okay, so I know I shouldn't be too bold. So, and the kernel has a density with respect to Lebesgue measure. Yeah? So this G epsilon. It's really not important that there's a density, but it's important that this is a measure which really has so it would be enough to have less than or equal to epsilon the entire mass, but this is a Markov operator, so we know that this total mass is equal to epsilon. Yeah? So that is, makes the life a little easier. If it's less than epsilon, it's also fine. That's a sub-Markov case, also possible. Okay, so now I do the following. Look, sorry, I'm trying to now convince you that this converges for epsilon to 0. So if this converges, you see if x is 0, now the initial condition is in L2, then this converges increasingly to L2, and this converges increasingly to L2. So I have exactly my equation that I want to have, that I used before in a non-rigorous way. Okay, so now let me, we just look at this term. So I call this x for the moment. So there are x here, and then I want to give you the estimate. Okay, and I want to put in this, and if I do this term, which I just show you, where there was xs here and so on, here was the xs to the power xs p minus 1. So if I do this, and I put in this thing, I get this. And now this is geared up for monotonicity. Yeah? So that, I mean, is really the heart of this convergence proof. So now you have exactly monotonicity here. So there's two variables, x tilde and xi tilde and xi. And now look at this. You can estimate this by zeta monotonicity from below by this guy, okay, with a square, yeah, and a minus sign. And then you can rewrite this as I came from here to here. I go backwards. In this case, you can rewrite it like this. And now this is just the Yoshida approximation of the corresponding Dirichlet form. So if epsilon goes to 0, this increasingly, so with a minus sign, decreasingly, converges to this object, but it could of course be minus infinity. So far I have not proved it's finite. If it's finite, then it follows that zeta of x is in H1. It's just a Yoshida approximation of elements in H1. And that is exactly what comes in here drastically. And this can be done in total generality. So that we will find out that zeta of x is really in H1. So that's the trick to the technical trick how to handle this. So in our case for p, so v phi is just p x times x norm to the power p minus 1. Then the zeta s is this, as I said before. And for p equal to 3, we get our old guy. Remember the gradient of x times x, what I had before. Okay, so now how is the logic? The logic is, if we can prove this converges for epsilon to 0, we put this to the other side. Then the right-hand side converges. This converges increasingly. And this to the other side must converge, must be finite, because there's a sign, it's positive. Yeah? This goes to something negative here. So it's always positive. So that means this goes to the other side. This converges, that and that converges. So this must converge. It's increasing. So really this must be finite. So the zeta x is in H1. That's the logic. So what is missing and that's the last thing I want to tell you, is to how can we prove that this converges for epsilon to 0? Okay? And then we are back to the heuristic proof. I said at some stage from this point on it's rigorous, and then you just repeat all the arguments there with Poincaré, blah, 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 and then you're done. So now let us look at this part. So I've already written here the limit in my equation, so I take the interval. Sorry, I go back once more. So now I write this in like this, and then I take limit here, limit here, limit here, limit here. This limit we can prove afterwards it exists. I've already taken it to show, yeah, so it will be this guy that comes out. Once I prove this converges, and that is the hard part of the work. And here Benjamin Guess, I want to stress this, really helped a lot with a very nice idea how to prove convergent of this object. And we should ask maybe Vasquez, maybe he knows this, but we had to do it by bare hands, by Galerkin approximation. It's not really difficult, but it is work. And then you can, so before in the non-rigorous proof, we just put the gradient to the other side and use the chain rule here, basically, which is not clear. But if we can prove this, that was the x to the power 3 before, is in H1, and I said we can, then we are done. And in fact, we can prove the following. The phi of x, in our case, is this, is in this space. Okay, and that's enough, because then we can do the integration by parts. And we do this, so this we prove by Galerkin approximation. Time is not enough to give details there, but so I just hope you believe me, we can prove this. Then you put the gradient to the other side, yeah, and then the phi is this, and then we are allowed to use the chain rule, because we also know this guy is inside. This is just a zeta of x, this we prove at the same time. Yeah? So if this converges, then we know it is inside, and then we can use the chain rule. So we can take out this part, and then remember we can proceed exactly as I did before. So now we separate this. This is in H1, this is nice. So we separate this by Young inequality, and then we separate this by Young, this makes this small, and put this in the minus part, and so on. And then the rigorous part of the heuristic proof from here on kicks in, and we get everything we want. So we put everything together. So we get this, and then, as I said, we can proceed as in the heuristic proof and prove the result. Yeah, so that is the difficulty. And now coming back to the multiplicative case, you have to do the usual transformation to get away the multiplicative case, which we all know from finite dimensions. And the deterministic equation you get is horrible. If the W depends on space. If it doesn't depend on space, if you put there just real numbers, so Rn value Brownian motion, not very physical, but you can do that. So that means you perturb your physical system by one random vector. I don't think it's very interesting. You would like to perturb a random function all over the space. Yeah? So if you do it with a random vector, no problem. It's completely trivial to handle that case. But if it depends on the spatial variable, you get a horrible deterministic partial differential equation. And we let it rest for half a year because we thought we can never solve it. And then last time I was here in January, so in fact also Viorel Barbou was working on this, so we worked on this together. And then last time in January here, I suggested another approximation. Brownian path is in there in this transformation, and it's not differentiable in time. So I suggested a certain approximation of this Brownian path, and then Viorel said, then it must converge. So he went back, came back with a proof. There were a few gaps. He went back, came back with a proof, and finally now I think we have a proof. And we finalized this on my during my last day in Pisa. So it seems we can really solve this horrible equation because a little bit of monotonicity is left. It's not monotone because you get terms, just to give you a feeling what happens. So you get nonlinear terms where you have this, if mu, let us call mu the Brownian motion here, depends on space and time. So on psi and t. And then you have your yt in here. Sorry, this was my notation. And then you have e to the minus mu outside here. So if the Brownian motion does not depend on psi, they cancel. Sorry, there is here some power. I don't know, for instance, power 3. So I mean, if there is a Brownian motion not depending on space, they just cancel. Everything becomes trivial. It's again a monotone equation. You solve it pathwise, end of the story. But it depends on psi. And these guys destroy monotonicity completely. So we had to find a new way to solve these things, but I think now I can announce that everything is fine. And then Benjamin Guess has all the other techniques to prove that we have also a random attractor in that case. But this is just being written up, and give him some time. It's his PhD thesis. Don't make him a hard life by competing with him. Just give him half a year, I think, then it's done. Thank you very much.
So in fact, again, I wanted to compare maybe the additive case and the multiplicative case. So so can you prove, probably I have the impression, if I understand well, that you have a criterion also to prove, to see if your random attractor is deterministic in some sense. No, because you said that you have somehow the distribution of the...
No, we just said in this other case that the random attractor is a random point.
Yes.
And the distribution of it is the invariant measure. So if you take this random point and you look at the Dirac measure at this point, and you take the distribution of this is exactly the invariant measure of the system. That's all we can say. It's not the deterministic.
The multiplicative case, in some situation, could you expect maybe that the attractor is deterministic?
I don't think in these for these models I would.
Because I mean, just
what you might have in mind, I know what you have in mind. If you take a one-dimensional case with a very singular thing here, for instance, you take the Heaviside function inside here, Heaviside function times identity, for instance. I mean, then we proved this is this paper in Communication PDE last year that you have what we call first level of self-organized criticality, because you can prove extinction of the process. And so you might be right that in such cases one can, you would expect, but you see it's not the forward, you always look at the backward random attractor, so technically it's not really the same, so one has to check. Though in the deterministic case, by the way, we prove only extinction with positive probability. In the deterministic case, of course, then it gets extinct in finite time, but otherwise only with positive probability. So I have not a very good feeling what happens in that case at the moment. But it would be nice to be able to show that.
Other question?
You worked very hard to get this exponential estimate in the space L2. There you also mentioned estimate in the space H. Are they equally hard, or?
No, this is much easier. These were the two equations, right? I only gave you the proof of the hard one, the first one. The second is easier. Yeah,
I'm asking because there is an alternative way to prove existence attractor without really using the compactness of the embedding which you use.
The compactness of the embedding is not so important. This is just to have this very nice explicit random attractor by this ball. I mean,
the question is...
the problem is the L2 norm, because that's not in L2 a priori. That's the technical problem that we have to deal with. Yeah.
You have also here L2 on the right-hand side.
We have it also on the right-hand side. So we have to do basically a similar thing with this approximation. So it's not completely trivial. You have to do similar approximations.
Do you have any feel for the topological the character of the attractor in terms of dimension or?
No. So I think the first thing one has to do is because in the classical case it's a point. It's first of all to work out really an example where you can prove it's not a point. That's the first thing, and then you can think about the structure. But that's the next step.
Other questions or comments?
So when, in the classical case, when zero noise, the Laplace of phi is a accretive in L1 or H minus 1, the Bryces. So those are the phis you are using?
Yes.
Right?
So yes, this is a very good question. Of course, this for random attractors, because it is technically difficult, and at other places you take, first of all, easier models. But if you go to the general model, which I mentioned, they have been handled in these two papers. The first one is in H minus 1. Yeah, so that means H minus, but we use all these spaces. So for instance, this V is the intersection of H minus 1. So this space is an intersection of H minus 1 with a properly chosen Orley space. And this Orley space comes from the phi, because the phi, if you take the integral of this, you get a Young function, and this you take for your Orley space. So that's the idea of this paper. The other one, with, together with Viorel and Giuseppe, we used really, not really L1 framework, but L1 techniques, because we wanted to cover the case where this is not continuous. And we didn't want to take any, because in the first paper we have polynomial bounds on the phi, otherwise the Allis theory is not so handy. And in that case, we can also take exponential growing function phi. So there's no bound on the growth. And there we use typically L1 tricks. So that means L log L, and then you get estimates, and then you get tightness and stuff like that. So that was very much along the L1 ideas. And also another paper Francesco is going to talk about on Thursday, the probabilistic representation of the solutions of the porous media equation using the singular diffusion approach. Also in that case, we heavily use in the singular case both approaches, the H-1 approach and the L1 approach, to get the best possible estimates. The combination of the two. Yeah. So it is technically quite involved to get this. And we see this porous media equation as a model case of these nonlinear equations in this, which are away from the usual ones that have been studied before. And this is one main motivation for this. May I add one thing before I forget? You might be not happy with this noise, because the most important thing for the porous media is the solution should be positive if the initial condition is positive, because it describes the density. So of course this is never the case here. But in these papers we study fully multiplicative, very general multiplicative noises, and in particular we study the case where we have linear multiplicative noise, and in that case we prove positivity of solutions. There's another paper in Indiana, it's also, well, this is wrong. The paper with Vernon Wang I think is in Journal of Differential Equation. This is a mistake, I'm sorry. There's another paper with Viorel and Giuseppe, which is in Indiana Journal, and there we prove positivity of solutions. So if the initial condition is positive. I'm sorry about this, so that is not there. It's in JDE 2007. It was just a mix-up from the publications.
I have a question. Are there any relationship between invariant measure and attractor?
Yes, so
in this case, I think there is a
definitely, you're absolutely right. I mentioned this already. So if we had this random attractor in the case, in the second theorem, so where we prove this is just one point, this is an easy example. It's more generally true what I'm saying right now. But then you just look at the Dirac measure and you take expectation of this. That's exactly the invariant measure. Yeah? So that's also, sorry, this is not true.
In my other world, this is called coupling from the past.
Right. But your world is not so far away, your other world. It's just the image of our.
Okay. More questions or comments? If not, thank you again.